Right now, we'll start talking about reaction mechanisms for inorganic or transition metal complexes. I'll start here by going over different types of reactions. All right, here we just have a generic metal system. We have a metal with some number of ligands and some charge on it. And simplest thing that a complex like this can do is lose one of its ligands, undergo a dissociation reaction. Or some complexes exist with two different stable number of ligands, and sometimes they can just pick up one additional ligand and undergo ligand addition. Often, the most common though is we do a substitution reaction where we lose one ligand L and we're replacing it with a new ligand labeled L prime. So one of the L ligands leaves and a new L prime ligand attaches. Later on, we'll talk about redox. Sometime next week, we'll talk about redox reactions where we either add an electron to or remove an electron from the metal center. And also we can talk about, this is one of the most interesting for organic chemists, is reactions at a coordinated ligand. Often these ligands, the properties of them are much different once they're attached to a metal center than the free ligands. All right, let's go through some examples of each. So substitution reactions are one of the most common, and it involves removing a ligand from the coordination sphere and bringing in another ligand to the coordination sphere. Without a change in the coordination number, so if we had 6 ligands in the starting complex, we would end up with 6 in the final complex, and no change in the oxidation state of the metal. So for example, we can take chromium hexacarbonyl, replace 3 of those ligands with triphenylphosphane, and so we've just brought 3 phosphanes into the coordination sphere and removed 3 of the carbon monoxides as gas. Here we could take this tetrachloroplatinate, remove one of the chlorides, remove it from the coordination sphere and bring an ammonia in instead. We'd probably do this by refluxing or boiling this complex with ammonia. Or here we have a tetraaquo copper complex, and we've replaced the waters being attached to the copper center with ammonias being attached to the copper center. The idea here is you should notice that we have 6 ligands coordinated, 6 ligands coordinated, 4 coordinated, 4 coordinated, 4 coordinated, 4 coordinated. So we're not changing the overall coordination number when we go from reactant to product for a substitution reaction. 2 and 3 that we're going to talk about are the stranger type of reactions, and these are kind of odd to find. We have to search to find some of these. A change in the coordination number occurs by decrease in the number of ligands. And here's one of those. We have this complex that has nickel with 2 ethylene diamines and 2 waters. This is 6 coordinate because the ethylene diamines are chelating ligands. They have 2 nitrogens on each, so there's 2 and then 2 more, so 2, 4, and then 2 oxygens. So this is 6 coordinate. If we heat this, we can drive off the waters and it goes to a 4 coordinate nitrogen, 4 coordinate nickel center here. Likewise, these addition reactions are pretty odd. We have to search pretty hard to find these. We have copper with 2 of the ACAC ligands. That's acetylacetone 8 ligands. These are also chelating ligands that both oxygens attach. This is a 4 coordinate copper center. If we heat this in solution, in a solution of pyridine, which acts as a ligand and a solvent here, we can form a 5 coordinate copper complex where the 2 ACAC ligands are attached, so that's 4 oxygens attached to the copper plus the nitrogen from pyridine gives us a 5 coordinate complex. Both of these are odd. Usually most of these complexes have a preferred coordination number, but occasionally we find something like this where this is happy to be 6 coordinate or 4. This is happy to be 4 coordinate or 5. Here's a preview. We'll talk about these later in more detail. Oxidation reduction reactions, electron transfer reactions. These simplest, we have ruthenium here. The ruthenium is in a +3 oxidation state. It reacts with chromium 2 to get reduced down to ruthenium 2. And in the process, of course, that electron comes from the chromium. So the chromium now is in the +3 oxidation state. Likewise, we have iron 2 here, and what would that be? Iridium 4. So iron 2, iridium 4. The iron gets oxidized now up to the iron 3 oxidation state, and the iridium gets reduced. Okay, we don't have any change in ligands or anything here. It's just simply an electron from the iron center popping over to the iridium center and reducing it. This is a special type of reaction, and we will head back in for one day back into chapter 13. We'll talk about this in some more detail. It is a oxidation. It is a oxidative addition reaction where we actually have a ligand, and when it adds, it changes the redox state of the metal center. If we go through and calculate everything here, we have, in this case, just a chloride. So this is iridium 1. When we add HCl, we have now 2 chlorides and 1 hydride. The whole thing's still neutral. And so it's gone from iridium 1 to now iridium 3. And so this process, when it happens, we're adding ligands, but we're also oxidizing. So this is an oxidative addition. Oxidative because we're oxidizing, addition because we're adding ligands. This is going from having 1, 2, 3, 4 ligands to having 1, 2, 3, 4, 5, 6 ligands. It's going from a 4-coordinate complex to a 6-coordinate. And then the opposite also happens. Here we have iridium in the +3 oxidation state. This is a different complex. +3 because it's a chloride and 2 hydrides. And it can release hydrogen gas. And now we've got just a chloride in the coordination complex. And so it went from iridium 3, chloride dihydride, to iridium 1, chloride, and released H2. We'll talk about both of these in more detail. And finally, we can have reactions at coordinated ligands. And the simplest here is when we have these hexaquo complexes, especially if the metal has a high charge on it, these become very acidic. The protons of the waters become very acidic, and so a base can pull off one of the protons. And what's happened here, you have to look very carefully, but it is not redox. It might feel like redox because we went from the +3 to the +2. However, it's a change at a ligand. So one of these waters, whichever one you want it to be, has lost an H+, and now we have 5 waters and 1 hydroxide. So hydroxide is OH-. This is still chromium 3+, and so 3 minus 1 gives us a +2, and we'll release a water. This reaction was very exciting at the time. We'll talk about this in more detail later. This reaction, we have a cobalt-3 center. We have 5 amines attached. This is carbonate, which is CO3 2-. That's how we get our +1 charge. This undergoes cleavage to give us a water complex. And there was a lot of work that had to be done to show that this oxygen from this water complex comes from the oxygen that's attached from the carbonate. There were extensive studies. A couple people spent their PhDs figuring this out. But a very, very, very weak acid can do this reaction if the carbonate is attached.